adhesion of the coating to a substrate is obviously key to its performance, and it's not something that we can easily predict, or in fact predict at all, through indentation. So this is a very useful complementary technique for indentation. So scratch testing, when performed properly, is another tool that should be regarded as essential. But again, it's got strengths and weaknesses. So an advantage is the fact that it can help us look at the coating adhesion, which, as we said, we can't do through the indentation method. Friction and acoustic data can also help us to identify the onset of the earliest failures. Okay, so very often the total failure of a coating system can originate from a small, seemingly insignificant failure, which starts much earlier. And for us to be able to identify the onset of these early failures is very helpful. Limitations, though, macroscale scratch testing is very commonly used, and that's a bit of a problem. So that scratch testing can be nano scratch testing, can be micro scratch testing, or macro scratch testing. So very often people are using scratch testers which are not well suited to thin PVD coatings. So they're using probe sizes which are hundreds of microns in radius, like 200 micron radius, for example, is a commonly used size. The problem with this is that it puts a stress maximum in the sample material which is too deep. It means what happens is the stress maximum is in a substrate. It's not in the coating or near the interface at all, which is really what we're trying to test. So very often scratch testing is not applied in the most sensible view. So we really should be careful about how we design our tests. It's a low strain rate test, so similar to indentation. It's subjecting the material to deformation at very, very low rates of strain, which are not reflective of the conditions that these materials will have to work under in the surface. Most scratch testers are room temperature only. So again, you know, we're missing slightly the optimum experiment design conditions. So what do we need for a more complete analysis? Well, we need to be able to characterize coatings under application relevant conditions. So for high-speed cutting tool coatings, this means, as we said, high strain rate, repetitive contact at the same point, and high temperature. So even more importantly is combining these things together, because in a high-speed interrupted cutting operation, we've got a repetitive high strain rate temperature with frictional heating. So if we put these things together on this little Venn diagram here, we've got this region in the middle. And this region in the middle is this combination of high strain rate, high temperature, repetitive contact. And that describes pretty accurately what a cutting tool experiences. So we need to be able to perform tests in this region if we can. How do we do it? Well, we can do it with a multifunctional instrument such as this NanoTest Vantage. So the Vantage is a multifunctional tool we've used in this study. It can perform nano and microscale indentation for measurement of hardness and plastic modulus, as we've already acknowledged is an essential tool in development of hard wear-resistant coatings. And we have nano and micro scratch and wear, and we've already identified that scratch testing is important. And really, for these types of coatings, micro scratch is what we want. We don't want to do very heavy, large-scale scratches where the stress maximum is in the wrong position. Nano scratch is too small a technique for these. Really, nano scratches for things like maybe up to around half a micron thick, something like that. So what about this high temperature, high strain rate combination? Well, here we can combine our nano and micro impact and fatigue testing with our high temperature capability that we have under our environmental control options. Put these two things together and puts us right in the middle of this Venn diagram. Okay, so this gives us a really powerful toolkit. We can establish fundamental properties of the coatings themselves. We can look at how the the adhesion of one coating compares to another with our scratch testing, and then we can do essentially what you might regard as an accelerated cutting tool type trial, cutting test type trial, the combination of impact and high temperature. So what is nano and micro impact testing? Okay, well, it's a technique that we developed here at Micromaterials quite a long time ago to help people to optimize impact resistance for very demanding applications. Typically, most of the coatings people are working with are cutting tools. So there are other applications as well, such as biomedical, implantable prosthetic joints, this type of thing. Anyway, this talk focuses on some cutting tool examples. So performing real cutting trial tests is quite an expensive and time-consuming process. It's expensive because it's time-consuming. It requires you to produce a finished cutting tool. It requires you to perform a cutting process on a suitable workpiece, then to stop, then to measure the wear on that cutter, then to continue cutting, to stop, to measure the wear on the cutter, and so on and so on and so on. And what you end up with is a lot of time spent. Yes, some quite useful information, but really then, you know, after the course of a day, maybe you've got one data set. So what you want to, what's very desirable is to be able to take coatings at an earlier stage of development, deposited in small quantities on a test piece, and then to perform some kind of lab scale test where multiple samples can be tested automatically with no user intervention, and they can give us a pretty good indication of what coatings we may want to develop further and put forward into a true cutting trial. It's important to note we're not trying to completely eliminate the concept of doing a true cutting trial. What we're trying to do is trying to pre-filter materials which we want to put to that more expensive and time-consuming application
Adrian,
test.
sorry to interrupt you, but your slide is not on the screen.
It's not on the screen.
Yeah, it is fine. Now it's fine because some of the participants said that it is not on the screen. It is on the screen. Fine. Please
you
go
can
ahead.
see it. Yeah, you can see it. Right. Okay. Yep.
Go ahead.
Okay, I'll carry on. So, how does it work? Well, this is nano-indentation. So there are similarities to nano-indentation. So nano-indentation involves taking a probe and loading that probe normally into a sample surface. As we said, it's the quasi-static test, typically maximum strain rates 1 per second, the absolute highest really. And we measure hardness, modulus, creep, etc. Okay, so low strain rate properties. So critically, what we've done is we've brought the indenter to the surface very slowly and carefully, precisely detected the contact, and then performed an indentation test. Impact testing is somewhat different. In impact testing, we're accelerating this probe from a distance away from the sample surface to bring it to the sample surface very rapidly to create a very, very high energy density impact event. Strain rates can reach as high as 1,000 per second. Now that's really a material dependent thing because, of course, very hard stiff materials will deform less easily, less rapidly than, say, a polymer, for example. In the case of the data in this study, we're talking maybe strain rates in the region of 100 per second on these hard cutting tool materials, and it gives us a different measure of properties. It gives us an indication as to coating toughness and resistance to fatigue failure. Okay, so it gives us different information than nano-indentation. It gives us high strain rates, toughness, and fatigue properties. So let's see. You know, how do we use it to relate to cutting tool life? So here we've got an example. We've been using this technique for about more like at least 15 years now. So we've got a lot of really nice examples of where the technique can be used as a really good indicator of performance. And so here we've got four aluminium titanium nitride coatings. They're quite thick, they're 8 microns thick, and they're on a tungsten carbide substrate. So some cutting trials have been carried out. Okay, so these are real cutting trials have been carried out. And what they're looking at really is the number of cuts they can perform under certain conditions before the wear on those cutters is deemed excessive. Okay, so this is real cutting results, and here are the corresponding nano-impact results. And what we use as a metric in our nano-impact test is typically the depth of the probe at the end of the impact test. So what we see here is this relationship between a small impact depth and a long tool life. It's kind of logical, right? There's been less damage in this sample, okay, with smaller impact depth and a better tool life. And then the other end of the scale, a much bigger, say, over 3 times deeper in terms of impact depth. And something a little over half of the tool life. So what's different about these 4 coatings? Because they are essentially the same material, but their structure is kind of different. So what I'm looking for, the morphology of the coatings is different. So this is how they're different. So this sample here, the one that gives the best tool life and the smallest impact depth, is actually a nano multi-layer coating. So there are 300 plus layers in this coating. Okay, they're all aluminium titanium nitride. One layer's been put down, then another, then another, then another. And what's happening is in these nano composite type coatings is that a crack can start to form. It can grow through one layer of the nano composite, and then the crack reaches the interface between one layer and the next, and that interface is sufficient to blunt the crack tip. Okay, so it actually can stop that crack from growing any further. Okay, so other cracks can grow underneath the surface, but they tend to be isolated from each other. So it takes a long time then to build up cracks that actually join together and lead to a complete failure. At the other end of the scale, we just have this one monolithic layer of coating material. There's no interface present other than the interface with the substrate. And yeah, there's a question coming from somebody there.
We will consider all the question at the end of the talk. Please go ahead.
Okay, that's fine. Yep. In the case of the multi-layer coating, there isn't any of these grain boundary. Not grain boundary. There are none of these interfaces present between the individual layers, and so the cracks can grow rather uninhibited all the way down to the substrate. And intermediate samples here have got different numbers and thicknesses of individual layers. Okay, so structure of a coating is important as well as just the composition. So this data here, this is nano-impact stuff. Everything we've seen so far, and this is all nano-impact. Some coatings, though, nowadays can be too tough to fail quickly, and we can't fail them sometimes in a time-efficient manner with nano-impact. So this is a good example. We've got 3 coatings here, 2 titanium aluminium chrome nitrides. So just consider these guys. So one of these titanium aluminium chrome nitrides has failed very quickly. So this is time. This is a 10-minute test. There's one impact every 4 seconds. So in this test, there are 150 individual impact events, and for each one, we measure the probe depth. And what we see in the case of the titanium aluminium nitride here with the 20% chrome, 70% aluminium, is a rapid failure. So we reach a big depth very quickly. The initial depth is similar to the other coatings, but the depth quickly increases. The other two coatings, however, the other titanium aluminium nitride and the aluminium titanium nitride, they do not show a failure event in the duration of the test. They just sit there at a constant depth. And we're using in this test 150 millinewtons, and we're using a cube corner indenter. I made the point that it's a well-used one because very, very sharp indenters can blunt in the first few impacts. So this tip has worn a little bit, but to the degree where its geometry remains quite stable throughout many tests. And so really this is defining pretty much the upper extreme of what we can achieve with nano-impact testing. As we can see, it's not capable of failing these coatings. So the conclusion is that we need a more aggressive and severe test. So what we've done is we've adapted our high load instrument. So this is actually our micro indentation head. We've adapted that for impact, and now we can impact with much higher forces. We can accelerate the probe over bigger distances, and we can deliver much more energy in an impact test. So we can actually deliver now up to about 100 times what is possible in a nano impact test. So here's some examples on hard cutting tool coating. We tend to use bigger probes. This is another benefit, is that we can use a big probe which itself will undergo less wear than a small probe that we'd use in nano impact. So that's really great because that helps to keep under control the rate at which we consume indenter tips. We're back to using a shorter duration test. Typically, we go for 300-second tests. As you saw in the previous slide, we'd gone to 600 seconds. We had no failure. So we try to keep tests in a 5-minute period. Typically, a 5-minute test would be 75 impacts. This is really the conditions that we prefer in order to do multiple repeat tests on multiple samples in a time-efficient manner. Impact loads go right up. As you saw, we used 150 millinewtons on the previous slide. Just here, 150 millinewtons. Now we can go right up to 5 newtons, and we're increasing the acceleration distance. In our experience, there is really nothing in terms of super hard, tough, wear-resistant coating. There's nothing out there that we can't fail with this. Okay. So this bigger scale technique gives us another opportunity, which is very useful, which is to use different sized probes. So in a nano impact test, we tend to use a small radius probe, and that tends to put the maximum stress point quite high up in the sample, actually inside the coating itself. And typically, very often, where a failure occurs is actually the interface between the coating and the substrate. So it's nicer if we can move this maximum stress point down a bit. So we can do that by using a bigger probe. Now, there are some existing macro scale impact techniques out there, but they tend to use a very big probe, in that, say, something like a radius of 1 millimeter. And there, the problem is all of our stress maximum point is right down deep in the substrate. It's too deep, so we've gone to the other end of the scale here. So we have limited sensitivity to what's happening in the coating. But by using an intermediate load range in the form of micro impact testing, we can also use an intermediate tip size. So typically we use something in the region of 10 to 25 micron radius tips, and that can allow us to put the stress maximum at a depth which is closer towards the region we're interested. Okay, so you can very easily change the probes to match what you're trying to achieve. So let's just compare the various techniques out there. There's nano impact, which is a technique we offer at Micromaterials. Micro impact, also a Micromaterials method, and macro impact. These macro impact testers are available from some other manufacturers. They work kind of differently. So just a quick comparison of them. Nano impact and micro impact both are depth sensing methods. We're using, so that means we're measuring the depth of the probe. Macro impact, on the other hand, what we tend to do is run the macro impact test and then perform microscopy at the end of the test as a post-test analysis. we're looking at time to failure. It's very, very clear when we get a failure event in an impact test. We get a depth step. We get an increase in depth. We'll see that shortly. So it's unambiguous usually to identify. So we can pick a time to failure. We don't really get that with the macro scale tests. The tests are short, okay? So 5 to 10 minutes, 10 minutes at the absolute maximum, really. Tend to use a diamond probe. You can use other probes, but diamond probes are prevalent in this type of testing. And tips from the region of 100 nanometers radius up to about 100 microns maximum. So there's a useful way to choose the right tip is to consider the ratio of the coating thickness to the test probe, and this kind of 0.1 ratio is about right. So these two techniques, the nano and the micro, give us a really high sensitivity to coating properties. But as we said before, when we go to macro testing, what we find is that the stress maximum is too deep into the material. We have low sensitivity to the coating itself. Sensitivity to adhesion, as we said several times now, adhesion is a really important thing in the performance of a coated system. And if we use a probe that's too small, we have limited sensitivity to the interface. Slightly bigger probe will give us more sensitivity, but too big a probe when we have no sensitivity to the interface. We can schedule multiple tests to be performed in an unattended manner, and there's some idea of the types of loads that people are using in these. So 0.1, so 100 million newtons to 5 newtons in an impact test. But we're talking about, well over 100 newtons in the case of a macro impact test. So let's actually use it now for something. So this is a case study. So it's two titanium, aluminium, silicon nitride coatings on a tungsten carbide, cobalt bonded tungsten carbide substrate. So both the coatings are on exactly the same substrate material. So the coatings are supplied by Huaqiao University in China. So they're both 2 microns thick. So that we have an analysis from EDX of the composition of the coatings. So they're kind of similar. And they were deposited with this silicon Balzers in a Venta mega system. So the difference between the samples is that one is a monolayer sample. This is the critical difference here. One is a monolayer sample, and so it's on this P30 cemented carbide substrate, 10% cobalt in it. The other one is also 2 microns, but it's a multi-layer coating. So it's 50 alternate layers of titanium aluminium nitride and titanium silicon nitride. Okay, so this is just a bulk layer of titanium aluminium silicon nitride. So that's the difference between the samples. Okay, it's a coating which is being developed for cutting and for forming applications. So it's being developed for use in applications where it's definitely going to see high strain rates and quite possibly high strain rates with high temperatures. So nano indentation of these 2 coatings at room temperature. So we used a NanoTest Vantage for this. So we're using 30 millinewtons load and of a Berkovich indenter tip. Okay, and we did some scratch testing as well, also with NanoTest Vantage, but actually with the high load head. So the nano indentation is performed with our low load head, and the micro scratch is performed with the high load head. We did some scratch testing for 5 newtons with a 25 micron radius diamond probe. So our nano indentation results are as follows. So similar hardness, there's 3 gigapascals difference there. The multi-layer is slightly stiffer, okay, than the monolayer sample. We can get some useful predictors out of nano indentation data as to we could use to try to predict how a coating might behave tribologically or in fatigue. So the hardness to modulus ratio is one indicator, and the hardness cube to modulus squared ratio actually can give us a useful measure as to how able the material is to deform plastically as opposed to fracture brittle. Okay, and so the suggestion would be that this nano multi-layer is actually likely to outperform the monolayer. Okay, now these relationships predictions don't always work perfectly because sometimes sometimes it's not the hardness and the elastic modulus that defines a coating's performance. So therefore, measuring those things and trying to use them as a predictor is not always reliable. But it's useful to then be able to perform the complementary tests, so the scratch tests and the impact tests, to work out whether or not these predictors are precise or not. If they're not precise, then there's something else going on with the coating we need to know about. So it could be an adhesion-related failure. So if we look at our scratch data, what we see is a critical load of failure. Critical load for failure with the nano multi-layer coating was higher, so it's 2.5 newtons as opposed to 2.1 newtons for the monolayer coating. So it would appear, that if we were going to predict from our hardness cube to modulus squared ratio that the multi-layer coating would perform better, it would turn out that was probably a reasonable prediction. Okay, so far we've got a nano multi-layer coating which is harder and stiffer than the monolayer counterparts. Critically, putting the absolute values to one side and looking at the ratio of one to the other, there's a suggestion in the indentation response that the multi-layer will be tribologically superior, and there's some suggestion from our scratch testing that that's a reasonable prediction. So, to the impact tester. So the impact test, we use a 17 micron radius conical probe. So this is actually a stereoconical tip. So it's a cone of 90 degrees that terminates in a spherical cap. It would have been a nominally 25 micron tip, but we measure these things very, very accurately, and this is actually more like 17 microns radius. We used various impact loads of 1, 1.2, and 1.5 newtons. One impact every 4 seconds for a 300-second period, so this is a 75 impact test. We're accelerating the probe from 40 microns away from the surface, and we've done several repeats of each test on each sample to get some statistical certainty. So this is what impact data looks like. Okay, so 1 newton, 1.2 newtons, and 1.5 newtons. So this is a monolayer coating, and with 1 newton, we see some initial plastic deformation on the first impact, which is absolutely inevitable, and then basically no events throughout the rest of the test duration. At 1.2 newtons, we get a bit more plastic deformation. It's inevitable because we're using a higher load, and at a certain point, we get some kind of, we think there's something happening with the substrate material actually, and then the depth starts to increase. So this is a typical kind of impact failure event. Stable behavior and then an increase in the depth. When we go to 1.5 newtons, then again, a little bit more plastic deformation than we saw with the lower loads, and then the onset of failure, in this case at about 20 impacts through the test. The nano multi-layer gives an essentially similar response, but its final depths are just a little bit bigger. Okay, so if we put them next to each other, you'll see that they're just on average, they're just a little bit deeper on the multi-layer sample than on the monolayer. Other than that, there's really not a whole lot to pick between them. So what we've done then is we have used a higher acceleration distance, a bigger acceleration distance. We've extended out to 60 microns acceleration distance. So that increases the velocity and therefore the energy that we're sticking into the impact. And now what we find is that this monolayer coating fails much quicker than the multi-layer. So we still get some low rate of deformation taking place for a period of time before our failure starts, whereas here really we get the initial plastic deformation taking place in the first few impacts, and then the failure is almost immediate. So there's some differentiation possible there between these samples and impact at room temperature. The conclusion being that the nano multi-layer coating survives longer than the monolayer counterparts. So there are some small negative depth steps as we saw. So you see just here it goes down slightly, and so these are usually associated with so initial cracking events and things taking place in the substrate. So as time goes on, we're investigating what causes these behaviors more and more by actually using focused ion beam and cutting down through the impact sites to see what's going on inside the sample. So here's some SEM images of our impact sites on the multi-layer sample at 1 and 1.5 newtons. So 1 here, 1.5. So the 1.2 newton tests were done afterwards because clearly the transition is somewhere in behavior is somewhere between 1 and 1.5 newtons. So let's look at these guys in a bit more detail. So here's 1 newton impact site on the multi-layer coating. When you look very carefully, you can see these ring cracks taking place inside the coating itself. If we compare this, unfortunately I don't have the image in here, but if I compare this with the equivalent on the monolayer coating, we actually had a few radial cracks coming out from the impact site as well, and that's a pretty good indicator that this coating is tougher, and that also corresponds with this higher hardness to elastic modulus ratio that we saw from our indentation. If we take a look at the 1.5 newton impact sites on the nano multi-layer coating, we can perhaps read a little bit more into what's going on. So here's just our normal secondary image. We can see this big area of removed coating, and then we've got this kind of slightly more grey material here. So what's going on? So this backscattered image allows us to differentiate between these regions a bit more clearly. So this light grey material is in fact substrate. Okay, so this dark stuff is the coating. We pushed it down. This is exposed substrate, and this is actually cracking running down through the coating. Okay, and so an EDX analysis of this material here confirms that that is in fact the substrate. We've got that pretty much exactly 10 weight percent cobalt that we discussed as being present in the substrate. So the monolayer coating, by contrast, at 1.5 newtons impact, actually it looks a little different. Okay, so we've still got some exposed substrate material going on here, but I think you'd probably agree that there's less damage spreading out from the impact site. So if we take the two images and we put them next to each other, and we use a circle here to define the true contact circle of the probe with the sample, we can see that quite clearly there's this much bigger fracture region present in the monolayer coating than there is in the multi-layer coating. Sorry, much smaller fracture region present than there is in the nano multi-layer coating. So we need to really be sure that what we're looking at here is not some difference just in the substrate. I want to get some assurance that it is the coatings that are different. These two substrates were the same as one another. If we take coatings on different substrates with micro-impact testing, we can actually identify the differences that they create. So we have so the substrate is an important factor. The substrate in the study is contrasted with another mono and multi-layer coating system. So these are the coatings in our studies here. So the crosses and the diamonds here are our coatings, and then these aluminium chronitride, titanium aluminium chronitride monolayer samples are on a different tungsten carbide material. Okay, so this is a tungsten carbide with a lower binder content, a lower cobalt content. And as you can see, what's happening is we get this much more stable, completely flat deformation going on, whereas we get this increasing deformation taking place here before the failure. If we zoom in on that, it's a little bit clearer. So you can see that this material with the lower cobalt binder content is actually giving a much firmer load support, whereas here we're getting some time-dependent creep type deformation with each impact event in the substrate, in the P30 substrate. So the good thing is about the impact technique is it's sensitive to the whole system. So it's sensitive to the coating, it's sensitive to the interface, it's sensitive to the substrate as well. Impacts at application relevant temperatures. So far what we've seen, just to go back a few slides, is that it would appear that in fact in high strain rate testing, this nano multi-layer coating is not performing as well as the monolayer coating in high strain rate testing. Yet it performed better in scratch and it gave us this higher hardness to elastic modulus ratio. So, the behavior is quite complex. That's all we know at this point. So it's good. It seems quasi-statically, but it's not performing quite so well in terms of high strain rate properties. So, moving onwards, impact at application relevant temperatures. As we said, these coatings are for use high strain rate and high temperature. And so there's this drive, as you can imagine, to make coatings work to make them tough and hard. Okay, so typically, of course, materials are either tough or hard, and so there's some conventional materials here. The stainless steel, for example, is a tough material, but it's pretty soft. You go to diamond, for example. Diamond is obviously a very hard material, but it doesn't have much toughness. So the real challenge here is to try to create materials which will exist in this part of the chart. So this is this desirable combination of hardness and toughness, but also at high temperature. So with our NanoTest instrument, we can perform tests at elevated temperatures. So we have a high temperature stage. So we can go up to nowadays up to almost 1,000 Celsius for this. In fact, some customers have published at 1,000. So we can do impact testing, scratch testing, indentation testing, etc. on one of these hot stage systems. When we're doing indentation, critically we heat the indenture as well. So this is an older slide now, but the 750 maximum temperature has been increased right up now to almost 1,000 C. And there's a special design feature on this high temperature stage, which means that the high temperature region is isolated to the sample and very close to the sample. So it's only this very small localized region that we're heating up. It's a very popular high temperature stage, and over 80% of published nano-indentation and nanomechanical analysis papers of high temperature nanomechanics papers are published using the micromaterials NanoTest hot stage. So it's by a long measure the most successful design of its type. So our high temperature scratch results are interesting. What we see is that the nano multi-layer seems to pretty much show a consistent critical load response throughout the temperature range that we tested. So we did room temperature 300 and 600 C. And the monolayer coating actually shows an increase in the critical load, and that's really because the material is behaving more tough. Okay, so it's behaving less brittle or more tough. So there's more plasticity possible before a fracture occurs, and that's why that's behaving better. Indentation is an interesting set of results. It's actually a very impressive performance that the coating puts up. So here you're seeing only about 30% drop in hardness over the range room temperature to 600 degrees Celsius. Okay, so that's pretty impressive. That's mainly due to the silicon content in the coating. And elastic modulus very impressively holds very steady. Again, I think that's due to the silicon content there. Often you would expect to see some hard coating types really drop very, very quickly in terms of elastic modulus. So both the coatings are maintaining their properties remarkably well in nano indentation. So what about our high temperature impact testing? Well, we performed tests at 300, 500, and 600 C, again with the same probe type. We used 1.5 newtons force and 40 microaccelerating distance. Other than the same, essentially similar tests. Tests were modified slightly because you want to reduce the contact time between the probe and the sample in impact testing at high temperature, because we don't heat the probe in impact testing, which means we can get a little bit of drift. So here's the results. So here's our monolayer coating, 25 degrees Celsius, 300, 500, 600 C. Something that's fairly interesting there is that the morphology of the deformed substrate material is kind of different. It's not fractured so much, so we're getting a lot more plastic deformation in the high temperature tests. But what we're seeing is the performance of the monolayer material is actually getting a little bit worse with temperature. Now, this is the interesting bit really, is the nano multilayer at 25 degrees Celsius was showing this great big fracture area. If you remember, we said it performs, it gave an impressive hardness to modulus ratio. It gave a good scratch test response. It wasn't so great in the multiple impact test. But what we see in our high temperature impact testing is that the extent of the damage that we see reduces with increasing temperature, and in fact there's next to no fracture at all taking place at 600 degrees C. So that's really quite impressive. So this coating, which appeared not to be particularly well suited to high strain rates contact measurements, cutting applications at room temperature, actually appears to be potentially a very, very good candidate material at high temperatures. So drawing towards a close, and various things we can look at in our we can look at the first impact depth, okay, for both the coatings, and we can see that the load carrying capacity of the coatings decreases with temperature. That's just because they're getting softer, okay? So we're heating the samples up, and the initial impact depth is deeper as the temperature increases, as you would expect. So the depth at which failure occurs is increasing quite a lot for the monolayer coating with increasing temperature, but staying pretty constant with the multi-layer. And looking at the final impact depth, we can see that the multi-layer coating actually shows a reducing final depth with a really rapidly reducing final depth with increasing temperature. And that's really because when we did the tests at room temperature, most of the failure was through brittle fracture. And now we seem to have a coating and a substrate system which appears to be able to evolve in terms of improved toughness and ability to undergo plastic deformation rather than fracture as the temperature increases. And that's really a very, very desirable thing. So this coating is this multi-layer coating is a great candidate for high-speed machining, high temperature. However, we have a problem that it does not behave well at room temperature. And of course, in the cutting process, you've got to go through a range of temperatures. The cutter will hit the workpiece and it will frictionally heat. So some of its cutting time will be at lower temperature and some of it at higher temperature, and it will cycle. So with some more understanding, hopefully, of what gives these coatings their properties, this high toughness can be extended across a wider proportion of the temperature range. So some conclusions on the room temperature testing. So the micro-impact testing extends all the benefits of nano-impact testing to thicker, tougher coatings, which we can't fail with nano-impact. It enables us to use larger, more rounded, we use the term blunt, it creates a bad impression, I'd say, but large radius probes and higher impact energies. And this is important because you don't want to be having to replace your probes all the time. So it makes micro-impact testing is a really nice, sort of easily, economically sustainable technique for sample testing. The energy we can deliver is much, much higher than with nano-impact testing. So we can see some pretty clear differences, load dependence differences between in the titanium, aluminium, silicon nitride coatings. At the lower load, the nano multilayer shows better load support and impact resistance, but at the higher load, it shows a lot more chipping outside of the impact site. At high temperature, we're able to combine our impact testing with elevated temperature to better replicate what's happening in a real cutting tool scenario. So we performed tests up to 600 C, and no obvious indenter wear took place. So as I said, it's a nice sustainable long-term technique. So both the coatings and the substrate soften and become less stiff. So SEM imaging confirms that brittle failure gets smaller at higher temperatures, particularly on the multi-layer coating at 500 to 600 C. And the nano multi-layer gives us better load support at elevated temperatures. Substrate softening plays a key role in impact wear at 300 C. So there you go. That's a technique which can interrogate these very, very high demand cutting tool coating materials at application specific conditions. So that draws me towards the end. So thank you very much.
Thank you, Adrian. I think you have completed your talk just on time. That is the 5 o'clock.
Okay.
Exactly in India, it's 5 o'clock.
Okay, great.
So we'll start the question answer session.
Yep.
There are 2 hands are there, 3 hands are there.
Yep, I can't promise to answer everything exactly. As I say, I wasn't involved in this piece of work, but I'll try anyway.
Dhala Chandra Mauli, your mic has not been associated with your device, so you cannot speak anything. So first of all, I request you to please associate your mic with your device. Okay. So I'm unmuting Ashok Kumar Abula. Please ask your question. Ashok Kumar. Yeah, please go ahead with your question.
Hello, sir. Thank you for the informative presentation, sir. So I have 2 queries about the impact testing and then the hardness measurement.
Yes.
See, you said that you have compared the indenter, what is that? The size of the indenter is affecting the stress at the interface as well as in the coating and then in the substrate, right? Can you explain how is it related? How the size of the indenter is related to these stress levels?
Yeah. Okay. Well, if you look at stress distribution, if you take like a two-dimensional section down through a sample at the point where the indenter's in contact, and you look at the stress distribution throughout that section, the point of maximum stress will be deeper into the material with a bigger radius probe. Okay. And so if you try to perform scratch testing or impact testing on a coated sample, let's say, a 2-micron coating with a 200 micron radius probe, you have very, very little sensitivity to your coating. Okay. Your stress maximum is very, very deep down the material. In fact, any plasticity that you might drive will probably start in the substrate first of all. So what will happen is you'll drive a very, very big scale deformation in your coated sample with too big a probe. And sure, ultimately you will fail the coating because you'll bend the coating and substrate system sufficiently that tension will build up in the coating and you'll crack the coating through tension. Okay. But any coating is going to fail if you do that to it. So what we're saying is that if you choose a probe which is too big, you have a test whose response is mainly going to be due to substrate behavior. If you have a probe which is far too small, okay, then your stress maximum will be very high in the sample. So if you took a 2-micron coating again, and you tried to use, say, a 1-micron radius probe, you would be essentially just scratching your way down through that coating. Or if you're doing impact testing, you would just be chipping little bits of the coating away. You would not be involving the whole thickness of the coating in the test response, and you certainly wouldn't be involving the interface. So very often, say probably 50% of the time, when we're doing impact testing or scratch testing, the failure occurs at the interface. The coating has actually remained pretty well intact until the interface fails. But you will not be able to drive a purely interfacial failure if you've got an inappropriately sized tip. And there are various metrics out there which can be used for helping to specify the size of probe you should use. And we in fact work with an external company called SIO, and SIO have a piece of software called Test Optimizer. And Test Optimizer is really nice for if you do a measurement, some indentation measurements of hardness and elastic modulus on your coated sample. So with a sharp Berkovich indenter. Okay, so radius is not coming into the issue with indentation measurements. And you do some measurements on the uncoated substrate, you could input these values into Test Optimizer, tell it the coating thickness, and it will suggest to you appropriate scratch test conditions, including the probe radius that you should use.
Okay.
Okay.
So, if will there be any effect of the stress which you apply onto this indenter? Like you said, if you change the area of contact area of the indenter, so that is deciding the stress level in the depth of the substrate or in the coating. What about the stress? The load, or what I mean to say is the load which you apply. Will it not have an effect on the stress generation in the substrate?
It'll have an effect on the stress level, okay. And if the probe is getting deeper into the material as you increase the load, then the stress distribution will change slightly as well, okay. So you put the probe on the surface and you start to load that probe up, and assuming that you've got relatively small deformation of the probe into the surface, what you'll find is
so we need to take care of both the dimension of the indenter as well as the stress or the load which you apply.
Oh yeah, definitely. Because I mean, this is So you'll find that there's some instinctive test condition selection that takes place. Certainly, when we get samples here at Micromaterials, we've usually seen something similar before. We know what we've used, was successful, so we've got a good idea of what probes we'll use. If somebody gives me a 3 micron thick coating, I'm going to think to myself, I'm going to use a probe something like absolute minimum 10 micron radius, but more likely a 25. If somebody gives me a 10 micron thick coating, well, I'm certainly going to start thinking about using a 50 micron probe. To specify tests at different loads is very easy. So often, we have an idea of what load range we might start with, and we set some tests up and see what happens. But more typically, what we would do is we'd say, well, let's set up some tests at 1, 2, 5, and 10 newtons, and just leave it to run, and then home in on where the sensitivity is. But or alternatively, as I said, we've got the benefit of the experience of having done these things before, and we're happy to advise people on a good starting point. But if you don't have the availability of that experience, that's where this test optimizer software comes in. You can put in what you do know about it from the indentation values. Critically, there the important thing is elastic modulus. So you perform the indentation measurements and input the measurement data files into the test optimizer software. Tell it what you want to do is optimize for scratch, and then it will generate a set of suggested testing conditions for you. Sure. So in reality, the interplay between these things is very complex, and so the algorithms in the software can cope with most coated systems and give you a useful starting point. Or you could just use this instinctive feeling that we have through experience, where we're indirectly taking what is really quite a complicated system and just say, well, in the past what we've done is this, and it's been about right. So yeah, I mean, like a lot of testing techniques, most time goes in just designing the right test, right? Once you've got the test designed, performing the tests is just routine.
So my last question is, so you have performed few the impact experiment, right? So are there any standards which you have followed? Because you said each impact, the interval between each impact is 4 seconds.
Well, this is the thing that there's for nano and micro impact, there is not a standard. There's no ASTM, there's no nothing. Okay, so because it's a new technique, it's still a new technique. In terms of age of a technique, it's still very young. It's starting to get some industrial acceptance now, so we have industrial users of this, particularly in cutting tools. So there are some standardized impact techniques, but they tend to be larger scale. But the problem with those techniques is that, certainly for thin coating application, is that they just do not have the sensitivity, right? That's the problem. So what happens is that it tends to work like this, right? What happens is industry or regulatory authority puts a testing requirement onto a particular component or device type. Okay, somebody's buying or using maybe in the aerospace industry, for example. And then something like an ASTM standard is drawn up, which relates exactly to that particular industry and that particular component. Then bear in mind that instrument manufacturers are very, very involved in making these standards. And what will happen is often then the end customer will go asking the manufacturer for a test to be performed in accordance with this ASTM. Now, it might not be the best test to do at the materials development stage, okay? So, for example, taking a 2 micron coating and doing a 200 micron radius scratch test might be useful to tick a regulatory authority box to say a test was performed on this to ASTM, whatever, and the results were within the expected range. However, from the perspective of a materials development activity, these tests are really uninformative very often. Okay, so the scratch testing in particular is uninformative in the same way as applying a standardized, more established macro scale impact test would be when trying to optimize toughness and fatigue resistance of a of a thin coating material. So you can do it, sure, and you might see it appear on a standard somewhere, sure, but it's not going to give you a great insight into what controls a material behavior.
Yeah. Thank you, sir.
Okay.
Thank you very much.
No problem. Okay.
Sir, if I conduct a micro impact test on substrate material which is of non-coated from the plot obtained from the micro impact test, can I predict or model the fracture behavior or KSE or JSE value? Material.
Yeah, you could, well, you could do through if you built up some build up some experience with that material type. Okay, so sure, we've done plenty of work with uncoated materials as well. So we've been doing some work on some tungsten carbide components for some oil pipeline valves, and it's quite interesting actually. There, in that particular case, what's happened is there's a manufacturer who makes these valve components. And the end customer who's making the valves is reporting variable performance depending on the grade of tungsten carbide used. There's an erosive wear problem that takes place. The manufacturer has attempted to differentiate between those tungsten carbide materials using the measurement facilities that they have. So, hardness, modulus measurement, fracture toughness, these sorts of things, and they have not been able to identify let's say a metric that they can measure themselves, which relates to this difference in behaviour that the end customer sees. When we perform the repetitive micro impact testing, then we get results which rank in the same performance order as the final products from the different grades of tungsten carbide, and we have then used SEM examination to establish what is different about the grades, okay, about the different tungsten carbide grades and how they're able to handle the impact loading. And yeah, the conclusions are, you have different sometimes inter-grain effects and sometimes different intra-grain effects. And so the answer, I think, is that with sufficient experience built up with the material type that you're interested in, then yes, you can start to see characteristic responses which might enable you to predict without going to the microscope or whatever. It might be able to predict what type of failure is occurring. Okay, but as I said to the previous gentleman's questions, is that it's a quite a novel and still fairly new technique, and so it's we're still doing a lot of learning out there. Which is really the attractive thing about putting it into a materials development environment. Okay, so it's giving us this insight, which it becomes increasingly apparent we can't get from other techniques. It really is filling a measurement gap, as it were, in the materials R&D.
Yeah. Okay. Thank you, sir.
Okay.
Will be launched just after the validatory function. So Prachi, are we ready for this validatory function?
Yes, sir.
So please proceed.
First of all, a very big thanks to all of you for making this FDP completely successful. Now I would like to request Professor Piyush Singhal, HOD Mechanical Department, GLE University, Mathura, to say something on the successful completion of first 1 week International Faculty Development Program online. Please, sir.
Thank you, Prachi. Really, this 5-day International FDP was wonderful. I have gone through various sessions and I found all the speakers were wonderful. Their talks were really insightful, and I am very thankful to all participants. I found them very enthusiastic throughout the sessions. Even your question answer sessions are very, very, very insightful. I am thankful to organizers, Kuldeep, his team, and my friends from Punjab University. And I hope that in future also we will organize such type of wonderful FDPs. Thank you one and all for your kind participation, and we will take the journey to a long way. And I request all to please take it as a way of networking with each other. I expect that we will connect with each other and will go to a long way with the knowledge of journey of knowledge. Thank you one and all.
Thank you so much, sir. Now, I would like to request the participants to share their experience or feedback about this FDP. If anyone is interested, can raise their hand. So, I would like to request Professor Argid RR to share his experience. Sir, I have unmuted your mic. Yes, sir.
Firstly, I would like to tell the workshop, this FDP was really wonderful. In future also, if in any such kind of FDPs are going to be conducted, I would like to be one of the attendees. It was like the one who is hungry for education or lifelong learning. This was the wonderful dish served by IIM, and I would like to thank Dr. Saxena too for wonderfully handling this activity. Thank you. Thanks a lot, sir. It was wonderful.
Thank you so much, sir, for your valuable feedback or experience. Now, I would like to request Gaurti Janardhan, sir, to share his experience.